we'll be discussing a few numericals related to current electricity, especially that being of Kirchhoff's laws. Now, in one of the questions, we wish to determine the net EMF of a circuit. This will be the first question, and the circuit being the combination of two cells in parallel having EMF E1, internal resistance R1, and the other being E2 with an internal resistance R2. Now, we had discussed the combination of cells in parallel, but in that case, if you remember, we had considered the EMFs to be the same while the internal resistance as well were the same in that case. And I had said that we'll be discussing uh, in the numerical section about the combination of cells in parallel with different EMFs and internal resistances, and this being one of them. Now, the potential difference across the points A and B, that will be equal to VA minus VB. Now, this may be giving out a current I1, and the other one, the lower one, may be giving out a current I2. We have considered that for ourselves for better results. Now, VA minus VB, that is simply equal to, considering the upper wire, we have the EMF E1 minus the current that is flowing through it multiplied with the resistance. Considering the sign convention, that will be negative because that is against our sense as we move from A to B, considering potential drop to be positive and potential gain to be negative. And so we have this to be I1 R1. Now let this potential difference that we have over here, let that be equal to V. Let us say that is equal to V. Now, so we have a V is equal to E1 minus I1 R1. If we wish to obtain the potential difference VA minus VB with respect to considering the downward flow of current, then the lower wire, that is, and in the lower wire we have a VA minus VB. So this is for the lower wire, and this one is for the upper wire consideration. And the lower wire, the VA minus VB will be giving me the values E2 minus I2 times of R2, that is the current that is flowing through it multiplied with the internal resistance, and that too is equal to V. So considering this, we have V to be equal to E2 minus I2 R2. With all these things available, what we can get over here is simply I1 is equal to E1 minus V divided by R1, and what about I2? I2 similarly is equal to E2 minus V divided by R2. Now I1 and I2, if they add up as they move along this circuit over here, that is I, and the current I is produced because of the net EMF across the circuit. Now if I draw an equivalent of it, what we have is there's an equivalent EMF that we wish to determine, there's an equivalent resistance that we have because of the internal resistances. We have the we have the current I, and we have the points A and B. Well, in that case, we will be having the equivalent EMF to be equivalent EMF minus I times of R equivalent, that is the internal resistance, the equivalent of the internal resistances in this case, and that will be equal to V, that is VA minus VB. That will be equal to V. We wish to determine this. Well, for that, what we can do is we just follow the procedure where so E equivalent is simply equal to the the sum of V plus I times of R equivalent. Or conversely, we can also write it as E equivalent minus I times of R equivalent is equal to V well we actually do not know this, we need this, we just want the I, and the current over here will be simply E equivalent divided by R equivalent minus V divided by R equivalent. Now if we observe these two values over here, we have I1 and I2, and from that we can get I. So on the left hand side, I is simply I1 plus I2, and that is equal to E1, we just add them up, E1 divided by R1, that is, I'm writing it separately for better uh, solving. E1 by R1 plus E2 by R2, the first two terms get added, and for V I can take V as common. I have 1 by R1 plus 1 by R2. What about this? Now the R equivalent, if you see, the combination here is parallel. So R equivalent simply 1 by R equivalent, that is the reciprocal of the equivalent resistance, will be equal to the sum of the reciprocal of the individual resistances. So here on the right hand side, if we have used the values on the left hand side from these two equations, we can have this equation for the right hand side, and we have E equivalent, which is to be determined, and there we have 1 by R1 plus 1 by R2 instead of 1 by R equivalent, minus V multiplied with those two terms, that is 1 by R1 plus 1 by R2. And if you see, minus of V times of this minus of V times of this, on both the sides they can get cancelled out. So what we have is E equivalent to be equal to E1 by R1 plus E2 by R2 whole divided by 1 by R1 plus 1 by R2. So this is the equivalent EMF for the given combination, given parallel combination of the cells. And well, if we wish to determine the value completely, then we can just solve it further for you to remember this quite easily. Well, you can remember this easily now as well, because you have the E1 by R1 to be the current, E2 by R2 to be the current. So current divided with the reciprocal of resistances giving me current times of resistance. So there's no problem with that. These two current terms divided by the reciprocal of the resistance is giving me current times of resistance, and so that won't be a problem. But from a simplification point of view, we can have E1, well, the R2 and R1 can have the LCMs. The LCM is R1 into R2, so R1 times of R2, and in the denominator we have R1 plus R2 divided by R1 multiplied with R2. They get cancelled out, the denominators in each part. So we have E equivalent to be equal to simply E1 R2 plus E2 R1 whole divided by R1 plus R2. So this is the equivalent EMF for the combination of cells in parallel with different EMFs, right? In another type, we may have a situation where we have the circuit to be like this, where the EMF is provided over here, a certain resistance over here, E1, this is R1, and then we have E2, and then we have an R2 over here, then we have an R3. In this sense, we wish to obtain the potential difference now between these 2 points, that is A and B. Now the potential difference in this case, if you observe the circuit, what we have over here is simply a parallel combination of cells between the points A and B with an extra resistance R3 from the previous case. I'm redrawing it in a better sense. So there we had the internal resistance. Here the resistance has been written separately. So this is R1, this is E1. It's exactly the same circuit with an additional resistance. Here we have R2, and then we have E2, and then this is between the points A and B, plus we have an additional resistance in between that is connected in parallel, and this is R3. Now again, if I may simplify this, we have E equivalent, R equivalent from the previous circuit between the points A and B, and then we have a resistance R3 over here. It's completely the same thing except for an additional resistance. Now the currents that will be flowing, that will be produced, supposedly are I1 and I2 from the two EMFs, and that will combine to give me I, and that I will flow through this R3 as well. VA minus VB can be obtained from the upper wire as well as for the lower wire between the points A and B. Going by the lower wire, we have this to be simply equal to the current that is flowing I multiplied with R3, I remaining in our sense can be taken as positive. We wish to determine this. What about I? Now the total current that is flowing across the circuit, if you observe it, then we simply can apply the Kirchhoff's law, and taking it in the counterclockwise sense, what we have is minus E equivalent plus I R3 plus I R equivalent is equal to 0. That gives me the total current that will be equal to E equivalent divided by R3 plus R equivalent, and we can just put that over here for determining the VA minus VB value. So what we have is a VA minus VB that we wish to determine in this case, that will be equal to the current that is obtained over here. This value, I am substituting the value of current over here, so we have this to be equal to E equivalent divided by R3 plus R equivalent multiplied with R3. Now E equivalent, as we have determined already from the previous circuit, is simply E1 by R1 plus E2 by R2 whole divided by 1 by R1 plus 1 by R2. This was the value of E equivalent. And over here we have some additional terms. Well, we have an R3 over there, and we have R3 over here as well, plus R equivalent. Well, that R equivalent, as you know, is R1 R2 divided by R1 plus R2, because this is not in reciprocal sense, so we are not really bothered about that. Now just to simplify this a bit further, what we get is E1 by R1 plus E2 by R2. We already have the result over here, but this does not look that good, so let me just have it in my own way, because we have all the datas that were provided to us: E1, E2, R1, R2, and then we have an R3 as well, but this looks a bit messed up, so let's just simplify that. We have 1 by R1 plus 1 by R2, let that be there as it is, and from this we have R3, R1, taking the LCM, R3, R2, and R1, R2 whole divided by R1 plus R2. We have an R3 over here as well. Now in that upper, in the numerator, what we have is E1 times of R2 plus E2 times of R1 divided by R1 multiplied with R2, that is the LCM part. R3 is there, it stays there. In the denominator we have R1 plus R2 divided by R1 multiplied with R2, and we had an R1 plus R2 over here as well, and this long term that is there, that is R3 R1, R3 R2, R1 R2, this, and that's it as of now. So these two terms can cancel out, these two terms can cancel out as well in the denominator. So we have a value over here which is equal to, let me write that here, over here for you. So we have VA minus VB to be equal to E1 R1, E1 R2, sorry, E1 R2 plus E2 R1 divided by this entire term R3 R1, R3 R2 plus R1 R2, and there's an R3 over here as well. If we wish to multiply an R1 R2 over here, I'll tell you why, we must divide it as well, R1 R2 over here. And doing so, what we get is, we get back our initial value E1 R2 divided by this R1 R2. The R2's get cancelled out, we have E1 by R1 plus E2 by R2. Well, that is settled from these two things. But what about this thing, the going down over here? So this thing going down, you simply have the combination of three resistances in parallel. We have 1 by R1 plus 1 by R2 plus 1 by R3, because in both the cases the R1 and R3's get cancelled out, we get R2, R3 and R2 get cancelled out, we get R1. If I write it in order, this is R2, R1 and R3. That's just the same thing. This is the net potential difference between the 2 points. Whether it be in this circuit, whether it be like this circuit, you always can determine the potential difference between those 2 points. In another form or another case, suppose we wish to determine the resistance. Well, let me just write the question for you. Here's a bit where we have a 4 ohm wire bent in the form of a square. Now this is a 4 ohm wire bent in the form of a square. We have the points as A, B, C, D, suppose, and what happens is that we connect a resistance that is from A to a certain point P, which is lying in between D and C, and the resistance here is 1 ohm. Now if we supply a potential difference between these 2 points, that is A and C, if we supply some potential difference, what we observe is that the points B and P will have equal potentials. VB will be equal to VP. So in that case, what will be the resistance across this wire, across this segment DP? The resistance across the segment DP, we wish to determine that. Let that be R. Now if we have this wire to be having 4 ohm resistance, uniform wire, then obviously bent in the form of a square, each segment must have 1 ohm resistance. This entire thing must have 1 ohm resistance. This entire thing must have 1 ohm resistance. Now with all these things, this value of R is taking some part out of that 1 ohm resistance, isn't it? So what remains, because resistance is directly proportional to the length, so with R gone, this value, this segment PC will have 1 minus R as its resistance value. So let me draw that circuit again for you. If we have B and P to be at the same potential, then what we get over here is that this looks a bit familiar to me, and this is the point B, this is the point A, this is the point C, and then from A we have a 1 ohm resistance over here. Between B and C we have 1 ohm resistance as well, and this A to the point P, and then from the point P to the point C, this is 1 minus R. And between A and P, what we have added is we have added a resistance 1 ohm over here, and what remains is A and D. They have been just merged together. Between A and P over this side, this segment, we have 1 plus R, because that remains in series now. And we had given a potential difference, certain potential difference, such that the potential difference between these 2 points. Now if we attach a galvanometer over here, this galvanometer shows a 0 deflection. That means Ig is 0, and this is simply the balanced condition of the Wheatstone's bridge, isn't it? So we have 1 divided by the equivalent resistance of this section over here is 1 times of 1 plus R divided by 1 plus R, R1 R2 divided by R1 plus R2, and the other side we have 1 divided by 1 minus R. So from this we get this can go over to the top over here, that is 2 plus R divided by 1 plus R multiplied with 1 is simply 1 plus R, 1 divided by 1 minus R. And from this we can just simplify this. So multiplying these two terms, cross multiplication, 2 plus R minus 2 R minus R squared is equal to 1 plus R, and that gives me R square minus R minus 2 goes to 0. Well, with this we can just obtain the value of R. R will be having two values, minus B. What is B? B is simply 1. Well, this is actually plus 2R, and this is minus 1. My bad, minus 1. So this is minus B plus minus B square, this being B, minus 4 times of A is 1, C is a minus 1 divided by 2, and what we get over here is a minus 2 plus the minus, this is 8 and this is 2. Now root over of 8 is 2 root 2, which is greater than 2, which is obviously greater than 2, and that minus 2 over here is going to give me some value. But what about the negative one? Well, the resistance can't be negative in the first place, and although it obstructs the flow of current. And this negative value, if I take the negative of negative of root 8, then that will be greater than 2, and that added with minus 2 will be giving me a value greater than 1 as well, and that cannot be the case over here because this resistance R is obviously less than 1, because the total resistance between the points D and C is 1, and a part of it is obviously less than 1. So what we get over here is we have to choose the positive value of root 8, so that is 2 root 2 divided by 2. So what we get is the 2's can get cancelled out, so we have root 2 minus 1. That certainly is less than 1, so that's a valid answer to this question. Well, that's all for this video. From this video, these are some of the examples. We'll be dealing with more of them in the upcoming videos on the numericals related to current, electricity. Till then, thank you for watching.